Thanks very much for inviting me to present my work in this Materials Interest Group seminar series. Today what I'm going to talk about some work that we have been looking at developing. Our objective has been to develop methods that can be used for modeling of materials. And in this case, we are interested in modeling of materials that also have electronic properties. So how we can combine the two different mindsets, two different field theories to get a unified approach to materials that as they deform, their electronic conduction properties change and their mechanical material properties change. So I'm going to present a hierarchical framework that we have developed, and we will be applying it to this particular class of materials. I would like to acknowledge my graduate students who have been the main force behind this work. Raghu Raman Kannan, who graduated in 2012, and Hari Shankar is sitting here. Hari, can you raise your hand? So he is currently working with me on this particular aspect. We have also had the luxury to collaborate with Dr. John Pask at Lawrence Livermore Labs, and over the years we have been funded by ONR and NAS, and the computational resources were provided by Exceed program. So here is an outline of what I'm going to discuss. First, I will present micro and nanomechanical material modeling aspect and hierarchical multi-scale framework for bridging the scales. Scales play a major role in modeling of materials, and unless we address the issue of scales at the material level, and at the same time we have computational techniques that are aware of the existence of scales, a fully comprehensive fully comprehensive solution procedure cannot be developed. So I'll talk about how to develop framework for this kind of applications. And then we will use modeling of nanotubes as an excuse to further enhance, develop this framework and look at its applicability, wherein we will embed nanoscale-based material moduli that will come from interatomic potentials. They will define internal variables that are going to be embedded in this particular framework. So there'll be quasi-continuum type of modeling where we will account for molecular mechanics ideas at the integration points, so embedded into the comprehensive framework. Now, quasi-continuum micromechanical approaches, these approaches cannot model the point defects, which in case of nanomaterials, graphene sheets or carbon nanotubes, defects could be in the form of vacancies. So these are in fact point defects. So how can we bring in that feature, effects which can be in the form of vacancies in this framework? So I'll describe that. That is one aspect of this framework. The other aspect is then electronic structure modeling, where we are going to look at a self-consistent solution of Schrödinger wave equation, and I will try to highlight what is new that we have done here, or what is the advantage of the things that we are trying to do, and using B-splines and Nerf basis functions rather than Lagrange basis functions, and what are the advantages of that, specifically for the case of Schrödinger wave equation, where we have potentials that are in fact function of the bond lengths and bond angles, and in the case of material which is uniformly deforming, those bond lengths and bond angles change, and that information is coming from here. Then how can we combine these together and develop a solution procedure? I'll show some numerical results and finally round off my talk with some concluding remarks. So here is a picture that has, I think it came from one of the NAS reports, and it very nicely presents or summarizes the effects of scales in the modeling of materials. So this is the length scale, and here's the time scale. And if you typically look at it, this is the axis along which we walk. If we stand here, these are the scales at which we do engineering calculations. If we walk back, we get to smaller and smaller scales. So as we get smaller length scales, these length scales are very tightly coupled with smaller time scales as well. So cost of computation becomes a major consideration. So continuum or continuum level modeling or quasi-continuum modeling lies in this end of the spectrum, and quantum mechanics, ab initio methods, molecular dynamics simulations lie at this end of the spectrum. This end of the spectrum, which is molecular dynamics based techniques, they are very good, and they can provide us information about the defects originating and sort of material degradation and so on. However, they are seriously limited in terms of the length scales and time scales if we want to scale them up to engineering applications. So from a computational mechanics perspective, important issue has been how can we combine these two, how can we bridge these scales? How can we embed these ideas but still be able to do calculations at the larger scales. And that has been one of the major issues in computational mechanics. What I'm going to talk about is mostly it will be in the range of quasi-continuum to micromechanical modeling. And so I'll be talking about this aspect here. So let's take a look at carbon nanotubes. As I said, that this is a medium that we are using to develop our framework. So if you look at carbon nanotubes, these are composed of carbon atoms, which are lying in a predefined hexagonal structure in here. This is not working, so I have to switch the pointer. Okay. All right. Okay, so they have perfect hexagonal structure. You can also think of them as graphene sheets, but rolled such that you get seamless cylinders. And the orientation in here gives different names: zigzag, armchair, nanotubes. If from physics, from a physical description perspective, they normally have single-wall nanotubes have 1 to 2 nanometer diameter, whereas multi-wall nanotubes go up to 25 nanometers. Their length can be 100 micrometers or even larger. Young's modulus, generally it's agreed that it is in the order of 1 terapascal. And these materials can undergo about 4% or more strain. Now, in the modeling of these materials, they highlight the issue of those length scales. For example, they have issues of both time scales, because flipping of a bond, vacancy appearing of a vacancy, defect, it happens at the level of picoseconds, while what we can actually observe in the lab is at a much higher level. Likewise, length scales, the bonds are in angstroms, and what we can see is at a higher scale, and we want to bring this information up. The effects of these switching back and forth, we want to bring it up to the level of a device. And atomistic simulations, although as I said, they provide very good information about all of this information of phenomena that are taking place, but they have difficulty going up to systems. For example, if you have multiple nanotubes, it'll be very hard to do it with atomistic calculations. So the idea is as follows. We want to develop a multi-scale method for micro nanomechanics, and the key idea is mathematical nesting of scales rather than doing brute force computational nesting. Computational nesting, we can always, it's a simple idea and can always be brought into play. However, mathematical nesting, that can be done if you can bring in analytical functions. They can certainly speed up your calculations. So that is what we'll try to see here. And this will provide us what we say hierarchical methods. Hierarchical methods mean that at final level, you have final constitutive equations, and the coarser level, you use homogenization ideas to speed up your calculations. And this nesting of scales, this key idea, will give us two systems of equations. It will give us a couple evolution equations that will provide us information about the bridging of scales, information at one level transferred to the next higher level. And it provides two overlapping domains. One will be a quasi-continuum domain that we will use for defect-free nanomaterial, and the other one is going to be atomistic scale domain that we will use to model the point defect, vacancy defects. So in the quasi-continuum model, we will use material moduli that are based on nanoscale-based internal variables, wherein we are going to use the stick spiral model that was proposed by Huajin Gao at Harvard and co-workers. And this is a kinematic model that, given the load, applied the load on a graphene sheet or a nanotube, how do the bond lengths and bond angles change? So it's a kinematic model. We are going to use, in that kinematic model, you can use analogy of linear springs or nonlinear springs. So we can use modified Morse potential, and that will provide us information about nanoscale based mechanical material properties that can be then embedded in this quasi-continuum domain. I'll describe that as we go on. And for the case of atomic scale domain, which will be used for modeling the point effect, we will use the idea that exists out there that has been used by physicists for a long time: formation energy of vacancy. What is the energy associated for making a vacancy, for kicking out an atom or a couple of atoms and creating a defect? What is the energy associated with that? Can we extract that force field? And if we can extract that force field, then we can use it to solve for the localized displacement field around that defect, and again, in here, we will be using interatomic potentials. So interatomic potentials are going to be fully integrated in both these scales that I present here. So let's first take a look at the molecular dynamics features for carbon nanotube hexagonal pattern. Here is 6 atoms. From a molecular mechanics perspective, we can write the total energy as a sum of these energy terms. This is bond stretch energy, bond angle rotation energy, this is out of plane rotation, this is torsional energy, van der Waals forces, and electrostatic energy. Now, this stick spiral model that I talked about, mentioned, developed by Hwaj and Gao, it is developed for axial deformation of graphene sheets or nanotubes. And the idea is fairly simple. They look at the first 2 energies. These energies are a function of the bond stretch and bond angle rotation. So think of it, this is like a hexagonal pattern in a nanotube, and this is the longitudinal axis. You pull it in this direction. If you pull it in this direction, these bond angles will change, bond lengths will change. So there'll be a moment induced and the force induced, and so provide a force equilibrium relation and moment equilibrium relation. In addition, this model provides an expression for axial strain in terms of, and the relation between axial strain and lateral strain in terms of changes in bond lengths and bond angles. So if we can find the changes in bond lengths and bond angles, then through these relations we can get Poisson equation out that can be put into our calculations. So in this framework, suppose we want to use modified Moore's potential. And this is, again, we can change it if you want to use Brenner potential, you could use that as well. So these are nonlinear springs in that framework. So the bond stretch energy and bond angle rotation energy is given here. Taking derivative of that with respect to delta R is a change in bond length, we get the force stretch relation. And taking derivative here with respect to delta theta, which is the bond angle change, we get the moment angle variation relation. Now we have these 2 nonlinear equations. We can substitute it back, let me take you back for a second, in force equilibrium and moment equilibrium relations, and we have 2 equations in terms of this applied force F, which is applied here. Substituting F from one to the other, we would get one equation which has delta R and delta theta, and this is a nonlinear equation. So we need to solve it, but we need another equation as well, because we have 2 unknowns, delta R and delta theta. So the other equation is provided by the stick spiral model, and that relates strain with delta R, delta theta. So now given a strain, we solve these 2 equations self-consistently at every integration point and pull out the mechanical material properties that then get embedded in the calculations. So we will be using this framework. Now that this framework is in place, let's take a look at what this multi-scale framework is. I've written here L of U is equal to L. This is an equation that models the deformation of the nanomaterial, not specifically just nanotube, just nanomaterial. L is the differential operator, F is the forcing term, and U is the unknown field. For the time being, let's say U is the displacement field. We can develop the standard weak form, variational form, by multiplying by appropriate weighting function and integrating over the domain. At this point, we make a multi-scale decomposition of the solution into coarse scales and fine scales. And if you want to get a physical feel of what these coarse and fine scales we mean here, coarse scales are typically measured to microscales. You can think of terms from -3 to -6 meters, and fine scales, micro to nanoscales, -6 to -9 meters. So we assume an additive decomposition of these scales. Since weighting functions are arbitrary, this lot is linear, so we can likewise split the weighting functions into its coarse scale and fine scale. In addition, we assume an additive decomposition of the forcing function into coarse scales and fine scales, and this coarse scale forcing function is what we will use for the deformation or modeling of defect-free nanotube, and F prime is the forcing function that we will use locally at that point around the defect. Question is how we will develop F prime, and I will talk about it later. So at this point, we assume an additive decomposition, and we substitute all of these back in the standard Galerkin form or standard weak form, and we get this system which is fully coupled in terms of scales. Now, this additive decomposition of F force into coarse and fine scale will further lead to a further decomposition of coarse scales into part of the coarse scale that is induced because of the coarse scale forcing function, and a part of the coarse scale displacement field that is induced because of the fine scale displacement field forcing function. And likewise, the fine scale displacement field has a component coming from coarse scale force and fine scale force. So U bar F bar and U prime F bar are coarse and fine scale components induced by F bar, and likewise these terms. Now I've shaded these colored them in blue. If you look at it, these are terms that are induced by forces at fine scale level, but they are affecting the displacement field at the coarse. So these are transferring information from one level to the other. I call them bridging scales, and I'll show how these bridging scales can be derived, can be developed. Now, so we substitute everything back into the system, and now we have much more complicated system than before. We have displacement field, coarse and fine. Each component could be induced by coarse scale forcing or fine scale forcing. Now, at this point, this is what we do here. So under this assumption of unique decomposition of the forces into F bar and F prime, which I will show for the case of nanotubes how we can do that. Under the unique decomposition of this, we can split this into a subproblem 1 and subproblem 2. This is one possible decomposition. If we add subproblem 1 and 2, we recover this particular equation. Now, even subproblem 1, which is driven by F bar, has these two components sitting there, coarse and fine, and likewise F prime has coarse and fine. Key idea is at this point. Consider subproblem 1. Since, as I said, that weighting function slot, whether this operator is linear or nonlinear, whether this equation is linear or nonlinear, the weighting function is always linear. And because of that, using the linearity of the weighting function, we can split subproblem 1 into its coarse scale and fine scale components. So you can see that this has been split into coarse scale, where the weighting function slot has W bars, and fine scale, where weighting function has W prime. And likewise, we can do with problem 2. So we have now segregated these problems. Now we are going to construct things back again. Our first step is going to be solve this fine scale problem and somehow extract an expression for U prime F bar that can then be substituted back into the coarse scale system, so that we can, when we solve the coarse scale system, the effect of U prime F bar is embedded. This step, which is shown by arrow, is what I call the modeling part of this framework. And likewise, this can be done for the second one. So we can construct, so rather than solving this with brute computer force, we can solve it back. We can plug this analytical expression back and solve the problem at these coarse levels. So we in fact will want to solve the problems at these levels. And so the step is solve it to find U prime F bar and U bar F prime so as to plug back. And I'll show you how we do that. So step A is, let's consider the fine scale problem driven by the coarse forcing. Let me take you back for a second. I'm talking about these red boxes. Red box number 2, solve it and plug it into the red box number 1. So if you look at the fine scale problem driven by F bar, considering that U bar F bar is the coarse scales that we computed, and if it's a nonlinear problem, it is coming from, we can pull it out from the previous step, and we can write this term as a residual, in a residual form. So we see that fine scale, this feature is emanating because of the residual of the Euler-Lagrange of the coarse scales. Once we get, and we can solve it over a small patch. If we know about the features of the solution, we can analytically do it. And we can embed that into the corresponding coarse scale problem, embed this term back in here. L star is the adjoint operator. When you plug it in here, this term has appeared because of U prime F bar. And if we get an analytical expression for U prime F bar, that will be the model for the fine scales. And likewise, we can do the same thing for the problem that is driven by F prime. And as I said, that this problem is going to be used to solve locally around the defect, and we will try to extract from it the local deformations in these nanomaterials. So the same problem, similar step can be done in here. However, F prime, which is a fine scale forcing function, and U bar F prime is coarse scales displacements induced by fine scale force. Now, this is not constant over the element. What we need is we need a larger space of functions, so solving this problem is rather tedious. For here, we will need to use numerical techniques to extract it, but keeping in mind that we are going to use it only around defects, so it means that we can localize this refined calculations only in certain regions of your computational domain. So coarse scale problem, and so this is our level 1 scale separation. This is level 2 scale separation, and now I'm going to show you results with both of them. So important feature of this formulation let me summarize the important features. This multi-scale decomposition of the forcing function provides two subsystems. A subsystem that is driven by F bar, which we call core scale forces, and this system is used to solve for defect-free nanomaterial. In here, we still have two steps. Step one is to solve the fine scale problem to extract the expression for this bridging scale and substitute it back into the corresponding core scale problem so that we do not unnecessarily do a lot of computations. If we have analytical tools, if we know about analytical tools, if we know about the feature of the solution, we can actually bring in and embed it into our numerical calculations. Likewise, we have a system driven by F prime, which is going to be solved locally around the defects. We do the same two-step process here. We solve for and find this fine component, and embedding them back into the system, we get the multi-scale formulation for the bridging scales. And as I said, defects in nanomaterials, the effects or zone of influence of defects is quite localized. So under reasonable assumptions, this problem can be solved over a very small region of the entire subdomain. So you do not need to do mesh refinement over entire domain. So problem driven by F prime can be solved over a much smaller subdomain. And total solution, if it is a linear system, if L is a linear problem, then you can get the total solution by principle of superposition. But if it is a nonlinear case, geometrically, materially nonlinear case, then we can employ Lagrange multiplier method for overlapping solutions. And this is what I will show we have embedded in here. So first is the case of mechanical properties of nanotubes, tube diameter, reducing the tube diameter, and his Young's modulus. Open symbols here, so our results are color-coded in blue. Open symbols correspond for armchair nanotubes, and solid symbols are for zigzag nanotubes. As we reduce, and we have used in this framework, Brenner potential and Moore's potential. Brenner potential is this triangles for zigzag and armchair, and the squares are for Moore's potential. And we get a response which is in this general range, and the reference results that have been published by Goes is an upper bound, and these others are sort of lower bound. And I want to again point out that these calculations were done on a scalar, on a scalar machine on a desktop. Here is Poisson's ratio, again, tube diameter. The blue colors are the results from this particular method using Brenner potential as well as Moore's potential. Zigzag and armchair nanotube, and we get a fairly decent correlation here as well. As I said, that main thing in modeling of these materials is the issue of point defects, and point defects could be in the form of, let's say, hexagonal pattern, but you see a pentagon in here, or hexagonal pattern and you see a hexagon. And it not only changes the local properties in here, it changes the local bond lengths and bond angles, but it also changes the curvature. But let's say we localize we look at what happens only around these defects. And these defects are mostly present by nature as well, or sometimes they are induced. For example, we have a nanotube with one diameter, another diameter, and sometimes we can induce these defects to go from one to the other, merge them. Or we want to change the chirality of these tubes, change their electronic properties. So these defects could be natural or could be induced in purpose. So these local defects in graphene sheets or CNTs induce an atomic scale, fine scale forcing field because the bond lengths and bond angles are not different. They are not the same as that of the virgin material. So question is, how can this be brought into the whole framework? So for that, we'll look at this F prime. We'll derive F prime. F prime is the fine scale forcing function, and our variational framework provides us this equation. Provided we can find F prime, this would provide us the solution around the defect and a variationally consistent solution. Okay, so F prime is going to be obtained as a difference of the energy minima for the defective and non-defective nanomaterial. And this comes about by looking at this example here. So we have a graphene, this is a 2D sheet, hexagonal pattern, and think that we are going to create a die vacancy. So these two atoms, which are color-coded in red, they're going to be kicked out. So when you drop them out, so there are two atoms that are less there. These bonds that were there, they are dangling bonds. Some new bonds will form, and the relaxed position of these atoms around this defect is not exactly same as in here. So question is, what was the force that was required to perform that? If we look at the energy of the perfect lattice, and let's say we use Brenner potential, where VR and VA are pair repulsive and attractive forces, the energy for all these atoms in here can be calculated as shown here. The formation energy of vacancy So is the energy of the relaxed defect-free minus the energy of the underlying two associated with the two atoms, because we have taken that out. That energy is not there. Those atoms are not there. Some bonds have disappeared, and new bonds have taken place, and the bond lengths and bond angles have also changed. So once we get the formation energy of vacancy, then we can get the average stretch energy by looking at the energy of the non-defective and the energy associated with the formation of vacancy. And keeping in mind that the defect-free nanomaterial is solved with the problem driven by F bar, so now we only want to solve for the energy associated with this vacancy or the defect. So once we have that stretch energy, taking derivative with respect to delta R gives us force stretch relation. This term has already been taken care of by the equation driven by F bar. So we are only interested with F prime, and that will be superimposed on the solution for the defect-free material. So F prime is obtained through atomic scale calculations by embedding these potentials in this framework. And we have used Brenner potential, but if you wanted to use other potentials, you can, in this framework, you can easily add that in. And based on that, modulus of elasticity and Poisson ratios are obtained as a function of changes of interatomic bond lengths and bond angles. So this is how F prime is obtained and the mechanical properties around the defect. But we still need to solve the problem around that defect. And that is done as shown here. So let's say this is the graphene sheet. In that sheet, lots of atoms, and there is a die vacancy, which I've zoomed up many times and trying to show here. So when we make the mesh, our first solve for the defect-free material, which is homogeneous material, almost like homogenized material. So we do not want to make an excessively fine mesh. So we can find a fairly crude mesh and get the calculation, but that calculation cannot see this defect in here. So we use the second pair of equations, which is I've again written in here, and we identify the element in which this defect exists, and this defect is much smaller than the size of that element. And that is the idea. We want to keep the calculations as coarse as possible while still being able to calculate the physics of the problem. So what we do at this point, in order to solve this problem, we create a submesh, identify the cell in which the defect lies, and then play the same game at that level. Since these defects have effects which are localized, so we can make reasonable assumptions under what is the proximity of this defect from the boundary of this patch, we can apply appropriate boundary conditions. So F prime is assumed localized around a point defect. So we create a submesh over the element that contains the point defect. The localized force field is evaluated over the defective cell, and we find the solution in this patch. And we get the total solution by applying Lagrange multiplier method for overlapping solutions. So we do not have to refine the mesh everywhere, and we are able to still recover that part of the physics. Here is nanotube with vacancy defect, and we are going to do comparison with Blechko and co-workers using these red dots and green dots are results from this particular paper. And this is based on density functional theory and other quantum mechanics calculations. And here are the results with light blue. These are our results, strain and Young's modulus. So Young's modulus drops as a function of strain. And what we predict is fairly in that general regime that is predicted by this density functional theory, however, at a fraction of a cost. These were done on a parallel computer, and all these other calculations were done on a desktop machine. This is the case for a CNT, 5,5 CNT with no defect. For the case of die vacancy that I just was talking about, again, strain versus Young's modulus. These are the results from the DFT theory. This is another quantum mechanical theory, PM3, and the results from our calculations are in this range. So this two-level scale separation seems to provide us a framework that we can isolate the defect, solve for the defect-free region, find the force associated with that defect so that we only solve around that defect using that force. Using the range of idea on the range of influence of the defect, we can limit or localize our patch and reduce our cost of computation. This is, again, stress-strain response, stress versus strain, no defect, and again, comparison with this DFT, and the blue dots are the present model, and here we have die vacancy defect, and generally in that regime. So this part, which was related with the mechanical aspects, micromechanical aspects, so nanomechanical aspects, can we bring in the defect that is at the nano level, but still want to use finite elements so that we can scale it up to, let's say, someday to, let's say, device type calculations. So consistency of the framework is an important thing that I want to highlight here. And this consistency of the framework is ensured by design of the method. Fine scale problem is driven by the residual of the Euler-Lagrange equations of the coarse scales. And F prime, which drives the problem, if during the calculations, let's say you have a defect and during the deformation, bond flips and let's say it becomes a non-defective material again, your F prime by default will become equal to 0 and this fine scale problem will automatically vanish. So it's a variationally consistent framework. And the splitting of the problem into coarse and fine scale subproblems also allows us nonlinear solution schemes with appropriate tolerance parameters. And this is also an important thing, because when we solve a nonlinear problem and we lump everything together in one solve, both coarse scales and fine scales, nonlinear equations are solved. We get out of the loop once the residual check is satisfied. And residual check is a function of epsilon parameter. And while we feel that we have got the solution to the problem, fine scales, if they are order of the epsilon, because they're fine, so they're much smaller than your main scales, so entire fine scales could be hidden behind the epsilon. So there could be an illusion that we got the solution, whereas fine scales may not actually get resolved. If you segregate them, then you can have fine scale tolerance parameters both for coarse scales and fine scales, so you can resolve each of these scales to a given or accepted level of accuracy that you want. And it also provides us a feature to use different time integrators at various levels. We have not exploited this feature yet, but this framework would provide us this feature for later use. Now, with this in hand, let's now take a look at the other part of the story, the electronic structure modeling. And in electronic structure modeling, we'll be looking at self-consistent solution of Schrödinger wave equation, which is again a quantum mechanical equation. And traditional techniques that have been used for solving this Schrödinger wave equation, they rely on Monte Carlo simulations or finite difference type methods. Our objective again is to develop variational methods. Variational methods have mathematical structures, and we can say a lot of good things about them. And I will show some numerical results in that context as well. So variational methods, and finite element is one such method. And plane wave methods are also there. However, we didn't want to use plane wave methods because there are certain limitations with these methods. Number one, plane wave limits the size of the problem because plane wave functions are global functions. They couple everything. And they lead to order n cubed system if we want to solve everything together. And these plane wave bases also have same resolution everywhere in real space. So they are inefficient for problems with local inhomogeneities. And these basis functions are limited to periodic boundary conditions. And these days, we see people doing playing with nanoribbons, nanowires. These are being conceived in next generation of electronic chips. So these, there are some works that are being done in the context of plane waves addressing this particular issue. Nevertheless, our objective was to look at variational methods, finite element type methods, because these can accommodate all types of boundary conditions, and the basis functions have local support, so it's very easily amenable to develop massively parallel codes. So although we want to use finite element framework, but we do not want to use Lagrange basis functions. That's why I put it at the bottom. Lagrange basis functions lead to C0 continuity. And C0 continuity means that your functions are continuous, but the derivatives are not continuous. And if you look at the electronic potentials, especially for the case of electronic structure calculations, these interatomic potentials, they are very smooth, but they're very localized. So if we walk along this path, and a lot of work has gone on Lagrange basis functions with C0 functions, but you have to resort to mesh refinement. And that is, once you start playing that game, it is a non-winning situation, because the more you refine, the other issues start kicking in. These functions also have Gibbs phenomena. The more you refine, you get Gibbs phenomena. And if you solve a nonlinear problem, this pollution catches up with you sooner or later. So instead of you doing C0 Lagrange basis functions, we opt to use B-splines and NURBS. And there are certain reasons. One is that B-splines and NURBS can represent arbitrary geometries accurately. Whether these geometries are unit cells, they are nanotubes, nanowires, all of these can be represented very, very accurately. So that is a major feature here. Another thing, that we can construct higher order basis functions with C1, or in general, Cp minus k continuity. P is the order of polynomial and k is the derivative across. So it means that we can, simply using these NURBS or B-splines functions, we can use Galerkin formulation and we can develop a higher order theory. So not only the functions are continuous, but the gradients are continuous. That is a very big advantage in terms of improving the accuracy of these calculations. So as I said, electronic potentials are smooth, but they're highly localized, and B-splines and NURBS are better suited for this kind of situation. And B-splines and NURBS have variation diminishing property, and this property helps in preventing from Gibbs phenomena from happening around the applications of steep gradients. So in my opinion, this feature of higher order continuity and variation diminishing property is the key deciding factor that we went from Lagrange basis functions to B-splines and NURBS basis functions. So let me give you a quick overview what B-splines are. This is a knot vector space. Knot vectors provide a parametric space for B-splines. Xi is a knot vector. These are real numbers, and distance between two knots in this knot vector space is same as a typical element in a finite element calculation, if you want to look at it from that perspective. Here, n is the number of bases and p is the order of polynomial. If the zeroth order B-splines are shown in here, and if p is greater than 1, then generic expression for B-splines is here, and the corresponding weights are here. B-splines have both H refinement. H refinement means that we can reduce the size between these knot vectors, or P refinement, which means we can increase the order of polynomial. So both the features that we like to have if we are developing a variational structure are present in these. In addition to P and H refinement, the important thing that B-splines have is K refinement feature. K refinement means the continuity of the derivatives. You can have higher derivatives also continuous across the inter-element boundaries. It becomes almost a nightmare if you want to do with Hermite cubics. People have used Hermite cubics. You get C1 continuity, but it's a nightmare to play with them. In B-splines, it's relatively straightforward. We do P refinement with lowest order polynomial mesh, then do H refinement after P refinement is done, and continuity of basis function is preserved through this process. So we get continuous functions and continuous derivatives. NURBS are nothing but B-splines, and the only difference is when the knot vector is not uniform, the corresponding rational B-splines are called non-uniform rational B-spline NURBS. NURBS have also H and P refinement and K refinement techniques, and using NURBS, you can locally refine in a region, and that is equivalent to do H localized mesh refinement in the context of finite elements. So, and higher order NURBS are obtained by tensor product of 1D cases. So now let's take a look at the pseudo-potential formulation of density functional theory. Cohen-Sham equations, they represent a problem of a particle moving, non-interacting particle problem moving in effective potential, V effective here. In this equation, phi is the complex valued eigenfunction, epsilon is the real valued eigenvalue, and V effective is the effective potential, which has 4 parts: local, non-local, Hartree, and exchange correlation functions. And these potential functions are quite involved by themselves as well. Now, if you are looking at the solution of periodic materials, then Bloch theorem, which is a consequence of translational symmetry of periodic materials, says it reduces the solution of Cohen-Sham equations to subdomain or onto a periodic unit cell. Considering that this is also periodic, so it reduces to periodic unit cell. And if we substitute the function, if we substitute this expression where V is the complex value function, in here we get the Schrodinger wave equation. K is the wave vector. And this periodicity of this complex valued function is applied at the boundaries. As I said, that the effective potential has 4 parts. Amongst them, the Hartree potential and non-local potential needs special care. This Hartree potential term where rho is the electron charge density, x minus x prime. So if you see, this has a term, 1 over r term, and it makes numerical evaluation of this potential computationally not very attractive. It's computationally expensive. And we see that a similar feature appears in local pseudopotential. So instead of solving this particular, doing this integral, we extract the Hartree potential and local pseudopotentials via writing an equivalent Poisson problem in terms of equivalent density. And that is what we have embedded in here. The non-local term extends over entire space over all atoms. Again, this is also very computationally expensive. But relatively recently, a paper by Pask from Lawrence Livermore Lab appeared, in which the idea of truncating these, introduction of projection operators that cut off the extension beyond a certain zone that has been applied and has shown that it doesn't degrade the accuracy of the calculations, but it substantially reduces the cost of computation. So these projection operators that are 0 beyond the cutoff radius, and this cutoff radius is based on how far is the potential influential. These projectors applied to separable pseudopotentials reduce the non-local term integration over all space to integral over unit cell. So we have truncated it to unit cell, Bloch theorem, reduce the solution onto a unit cell. So now we can solve the problem on a unit cell and write these properties. So here's the weak form or the Galerkin form for the Schrödinger wave equation. Here's the space of functions. So we are looking for H1 omega space, and periodicity of this complex function is embedded in this space. So our objective is develop numerical schemes so that we can find the scalar real eigenvalues and this function V such that this equation is satisfied. So if we look at this equation, this gives rise to a complex valued generalized eigenvalue problem. And here, the stiffness matrix that we calculate has, because of this term, has non-local term, and this non-local term needs special processing. And it also contains nonlinear terms due to exchange correlation potential and Hartree potential, which means that this is not just one solve. We need to solve it in a self-consistent fashion. And I'll outline the self-consistent solution procedure. So here is the self-consistent solution procedure. So say we have an electron charge density based on which we develop the effective potential that we are going to use in the Schrödinger wave equation. This effective potential has 4 parts. Out of these 4 parts, local and Hartree are obtained through solution of a Poisson problem. We calculate these, plug it into the system, form the stiffness matrix, mass matrix, solve this system, complex eigenvalue system, and obtain eigenfunctions, eigenvalues, where n represents the nth eigen solution. Once we have eigenfunctions, we can obtain the electron charge density. The new charge density can be compared with the previous one between successive iterates. And once we have uniform convergence, once we get it up to a certain convergence, mutual convergence between successive iterates, we can exit from that step. So we find the norm of error in the electron charge density and repeat the process until convergence. In these calculations, we have used Pauli mixing scheme, and we have used history of 5 densities to calculate new density to improve convergence rate. So these are very delicate and also expensive calculations. So here is a simple problem. This is chronic Penny problem. It's an idealized quantum mechanical system consisting of infinite periodic arrays of rectangular potential barriers. And we are going to use it to look at the mathematical attributes of our method. Mathematical attributes means that does it have H refinement and P refinement capability? Because we were interested in developing a variational form, variational method. Variational method has lots of mathematical attributes. One of them is, does it give you a converged solution if you do H refinement and P refinement? The potential is given in here. This diagram is the band diagram for B-splines order 2. These are the wave vectors and energy. Solid line here represents the exact eigenvalues, and dots represent the computed eigenvalues, and we get a good correlation amongst with the exact values. Here is the convergence rate for B-spline order 2, and so as we refine, as we reduce the knot space, refine, or in the context of conventional mesh, this will be your mesh refinement. As you refine the mesh, the error in this is defined in here reduces. And what we have plotted is both Lagrange and B-splines, Lagrange quadratic and B-splines. And we see that Lagrange and B-splines, they are all giving us, for quadratic, the convergence rate should be 4, and we are getting that slope of 4. This is a simple enough problem that we can see these features. And convergence rates for NURBS order p equal to 2, and again for NURBS we get similar convergence rate of 4. If we order elevate B splines and NURBS to order 3, then rate of convergence should be 6, and we see this slope of 6. Now in here, it seems like that for example, this triangle corresponds to the first eigenvalue using Lagrange, and the absolute error is less compared to for example, B splines or NURBS, which is this solid triangle. Let's say B spline order 3 seems to have a higher order compared to Lagrange, which again is counterintuitive. We wanted to do B splines, and I said that B splines are more accurate, but we are getting the rate of convergence, but the absolute error is higher. However, we need to look at this problem in terms of cost of computation as well. For example, this mesh for case of Lagrange, the coarsest mesh for order p equal to 3 has 28 degrees per direction, whereas for the case of B splines, the finest calculation in here, which is 18 by 18 by 18, has 23 degrees of freedom per direction. So these calculations with B splines are cheaper than these calculations with the Lagrange functions in terms of cost of computation, and considering that there was no bent geometries in here. The next one is Schrödinger wave equation, silicon analytical potential. This figure here shows conventional unit cell. This is the primitive unit cell. This is the first brilliant zone, and this is the irreducible wedge, and we do integration in this irreducible wedge. I'm going to show you the band gap. Band gap is just the energy range in solids where no electron states can exist. And these represent the energy difference between the top of the valence band and the bottom of the conduction band. And I'm going to show comparison with plane wave calculations, and these calculations were provided by John Pask in a paper, and we got these from him, but they were published in a paper in 2005. I'm going to show you the energy versus the k vector. And solid lines are plane wave calculations. 4 by 4 by 4 is equivalent of a cruder mesh, and then mesh refinement, 6 cubed, 8 cubed, and 10 cubed using B splines order 2. And we see here that as the sort of mesh is refined, we converge to the plane wave calculations. Same feature, we see similar feature if we order elevate B splines to 3. So H refinement feature for order 2, for order 3. But if we just focus on 4 by 4 by 4 calculations for order 2, which is this here, as we go to order 3, it is very close to the plane wave calculations. So between these, it has both H refinement feature, but case by case basis, you can see it also has the P refinement feature. If you keep the mesh the same, order elevate the polynomial, you will get the P refinement. Now here is gallium arsenide. This has a structure which is similar to silicon with arsenic atom in a location, so the vector is slightly different, but generally the structure is the same. It is FCC crystal. Again, energy for different K values. Band diagram along symmetry lines for first brilliant zone. And we have used HGH pseudo-potential and Perdue-Zunger potential for exchange correlation potential in these calculations. Numerical integration, 44 points in the irreducible brilliant zone. And we get a band gap of 0.024234 atomic units for B splines order 2. And as we order increase to 3, we get a band gap of 0.0184, whereas plane wave methods predict a value of 0.173 Hartree atomic units. Again, these calculations were from Pask. Here, using NURBS for the same calculations, now using NURBS, and we get similar profile, fairly resolved solutions where NURBS order 2, order 3, and comparison with B splines, order 3 that I showed you comparison with the plane wave calculations. This is the case of graphene. This is a 2D structure. This is unit cell. This is the irreducible brilliant zone. It is a one atom thick flat layer. We need 110 K points in the irreducible brilliant zone for integrating the electronic charge density, which is then plugged into your potential, which then drives the system. This figure is the band diagram for various order B splines. This is P refinement feature, P equal to 2, 3, 4, 5, and we see that between 4 and 5 we get fairly resolved P, pi, and sigma bands. One way of looking at the accuracy of the method is, we can use it as a measure of accuracy, is the energy of the system. So plane wave calculations, total energy of the system is shown here. If we keep the mesh resolution same and order elevate the polynomial, use B-splines and order elevate from 2 to 3 to 4 to 5, we see we converge from 11.27 to 11.33, which is close to 11.37 of the total calculation. Or if we keep the order of polynomial the same, if we keep the mesh the same and increase the order of the polynomial between 3 and 5, keep the mesh same order polynomial, we again get convergence. So even for this situation, calculation in which fully consistent loop is being used, we preserve those P and H type of refinements. Martin, how much time do I have?
5 minutes.
5 minutes. Okay, I will wind up. Yeah. So I will wind up here. So I'll show you a couple of results for the case of flexible and stretchable electronics. There's a lot of work going on at University of Illinois, Professor John Rogers' group, and I'm pretty sure there is work going on in mechanical engineering. People are looking at stretchable electronics, materials that can retain and enhance their electronic properties as they undergo mechanical deformations. So if stretchable electronics is your objective, then you have to characterize these materials in a high strain environment. Whether it's intelligent textiles being used for diagnosis of sleep apnea, or flexible sheets mounted over the brain to measure abnormality or record abnormality of skin patches, to monitor heart rate. All these are sensitive to their geometry. So electronic properties change rapidly. And if you are looking at it from a stretchable electronics perspective, the idea is that if you forcefully pull apart the material, then the electrons that flow through them will pass with less impedance, which means faster electrons, faster electronics, less power consumed, less heat. So both these features require these materials or a method that can characterize these materials in a coupled fashion. And that is an issue, and I'll come back to it in a second. So, and graphene is also being used, being conceived as a material for ultra-fast photodetectors for optimal communication. So question is how to combine these quasi-continuum based models, mechanical, with quantum mechanics based techniques for Schrödinger wave equation, considering that these are different mathematical and numerical, they have different mathematical and numerical attributes, and the solvers, the techniques to solve them are also different. Obviously, the simultaneous solution via monolithic scheme, if possible, is not going to be computationally optimal or software-wise manageable. So at this point, what we are doing is the kind of experience we have with fluid structure interaction problem or thermomechanical. Idea is partition or staggers that are spatially and temporally discretized for the underlying methods. And this strategy can simplify implicit, explicit treatments or load balancing or software modularity. So the idea is here. And this is a very simple one-way staggered procedure where we solve the micromechanical problem. It gives us changes, and so we are solving for this problem. We get the equilibrated state that gives us the updated interatomic bond lengths and bond angles, which then define the potential for the electronic calculations, and we get the electronic properties. So this is calculations that we are doing is on one-way coupling where the mechanical field, micromechanical field is dictating the electronic field. We have not yet been able to get to the point where we are feeding this back. Feeding it back would make it more robust. However, cost of computation will need to be looked at. So last example problem I like to show is strained electronics. If you have silicon on germanium buffer, if you deposit silicon layer on silicon germanium buffer, because of the difference in the force between the surfaces, it induces a biaxial strain. So we have this strain field where the components 1, 1, 2, 2, 3, 3 are given in here, where C1, 1, and 2, 2 are the mechanical coefficients like the Poisson ratio. The lattice coefficients, constants for silicon germanium, and the lattice vectors are defined in here. This is the case for silicon germanium, where germanium is 0.4, fraction of germanium is 0.4. Here's band diagram, and we see that the conduction band, we see a split along the symmetry line X and Z in the brilliant zone, and we see this symmetry being broken here. And we look at the band gap as a function of adding more germanium in this silicon germanium alloy. we see as we increase it, the band gap decreases, the conduction properties increases, electronic conduction properties change. So we can classify material. And typically these materials, the smaller you go, faster they will run. They will be heat produced. And so the strains, no matter how small they are going to be, the operational electronic characteristics of these materials are not going to be same as that of the ground material. So we'll need to, one will, some point in time, will need to have methods that can characterize these electronic materials as a function of strain. And these are two different schools of thoughts, and question is, need to bring them together. So as my concluding remarks, I would say, what I've tried to do here is we have developed a hierarchical multi-scale framework for bridging the gap between molecular mechanics and quasi-continuum mechanics. But rather than using brute force or doing computational nesting of scales, computational bringing the information from fine to the coarse level, we opt, or we like to do it using analytical functions as far as possible, because they can rapidly speed up they can make your calculations, increase the speed of your calculations. The two-level scale separation, it leads to a coupled self-consistent system of equations, and this is very important because we do not want to double count, or we do not want to ignore something. So this system has to be self-consistent amongst each other. And material moduli are based on nanoscale internal variables. Some ideas that we have used here are the ideas, kind of ideas, internal variable formalism that people who are familiar with elastoplasticity would have seen. Internal variables, those never appear directly in your system, but they are in fact defining your system. And evolution of the internal variables also needs to be done very, very carefully. Reason? Although we are always keeping an eye on the computed solution features, and we always look at that, but we do not look at the field that is created by these internal variables. And if there are ripples in that field which we never see, your computations will become unstable. So these internal variables also need to be updated in a consistent fashion. Formation energy of vacancy, we employed this idea that exists out there in physics, and used it to extract the fine scale force field, which we then embedded in here and to solve the problem locally. The resulting finite element method, it concurrently feeds information at molecular scales into your quasi-continuum equations. And this variational framework, and I've also showed this framework for quantum equations. We wanted to develop a variational framework because if you want to develop a coupled solution procedure at some point in time, then at least, even though you are coming from two different points of view, micromechanics and quantum mechanics, but if you have variational structures employed in both of them, then the coupled solution, that procedure that you develop, you can still talk about you can still develop some mathematical properties of that particular algorithm. We have opted to use B-splines and NURBS rather than Lagrange polynomials for the reasons that I explained. They have K refinement feature. They have variation diminishing property. Higher order functions can be used to model high gradients, and they do not suffer from Gibbs phenomena, which Lagrange polynomials suffer from. And compared to plane wave functions, B-splines and NURBS are local. They have local support, which means we can parallelize this code, whereas parallelizing a plane wave code is very, very hard. B-splines and NURBS provide the same features as far as parallelization is concerned as you get from Lagrange polynomials without having the disadvantages of Lagrange polynomial. So currently what we are working on is looking at coupling algorithms for integrated modeling of mechano-electronic properties under high strain environment. So this is something that we are trying to take this work. This is more or less a work in progress, that some parts that we have done and some parts that are going on. All right, thank you.